Hey everybody, my name is Ben Hovey, and this is my Physics Lab 5 about a falling Slinky. The purpose of this lab is to validate the physics principles that govern a stretched Slinky dropped from static equilibrium by comparing its observed motion, which we use to through tracker, and then with its predicted motion through GlowScript. The lab results are as such. The momentum principle was supported by the lab, and the predicted motion was very similar to the motion observed, which constitutes positive lab results. So fundamental principles. Of course, we have Newton's second law, aka the momentum principle, which states that systems' change in momentum is proportional to the net force applied. From this Newton's second law, we can get the position update formula, which will be very crucial in our coding, and the velocity update formula as well. The drag force, which states that it opposes the direction of a moving object, is as such, and the drag force will be in the positive direction, the positive y direction to be exact. The force of gravity acts in equal and opposite magnitude of that of the tension force, so the force of gravity will be down, and G will be negative. Some initial conditions. Well, of course, the system is just a Slinky, and the surroundings are going to be the Earth and this man holding the Slinky here before it is dropped. The initial position is as such 8.53 times 10 to the negative 3 meters, and that's in the x direction, and then 6.93 times 2 to the 10 to the negative 4 meters, which is in the y direction, and this is our initial position right here. The initial velocity is 0, so it's held in static equilibrium, and the mass can be roughly estimated to 0.21 kilograms, and the gravitational constant is 9.8, and that will be in the downwards direction. Here's our tracker, so I plugged this video into tracker and just tracked each point and gathered this data right here, which I then am going to compare to with my GlowScript or computational model. So this is my code that I used to develop my computational model. This is the mass of the ball that we plugged in, and here are the initial conditions for position and velocity. Here is where I plugged in my gravitational constant and the B, which is this right here in the drag force equation. And this is the direction that the B will point, or this is the direction of the force of drag. Okay, here's my computational model continued. This is going to be the gravitational force. This, of course, opposes, F tension is in the negative gravitational force direction, or in the positive direction. And originally, we just have two forces acting on the object. That would be the gravitational force and the tension force in the Slinky. And of course, here is the velocity update formula and the position update formula. However, after the top of the Slinky reaches the bottom, we now have different forces acting on it. We have the weight force of the Slinky, and we have the drag force now, as there is no tension force anymore since the Slinky is completely compressed. Of course, we still have the velocity update formula and the position update formula. After getting all that data from tracker, we can plot it against the computational model's data, and this can give us an observed versus predicted graph. So right here we have the predicted numbers, which is in the red in the computational model, and then the observed is in the blue, and that is the actual data that we collected. And as you can see, they slightly differ as we move along the graph. Some possible errors or reasons for this are external work. In reality, the system is not isolated from surroundings. Therefore, there will be external work done on the system. In this case, an example could be wind or any applied force, which could be as well as the man initially holding the Slinky. He could have put some applied force down when he was letting it go. Human error could also be a possibility, as I definitely made mistakes when placing the center of mass using tracker. So what if? What if we put a large weight at the bottom? Would it remain stationary? Well, the Slinky will remain stationary as long as the tension force within it counteracts the force of gravity, a condition influenced by both the Slinky's length and its spring constant, or its rigidness. This balance ensures that the downward pull of gravity is perfectly matched by the upward tension, maintaining its equilibrium. So in reality, no matter what weight or size we put on the bottom, as long as the tension force in the Slinky can be equal to the gravitational force, the Slinky at the bottom will remain stationary until it is fully compressed. Why does the bottom of the Slinky remain stationary? Well, the Slinky functions as a type of spring with internal tension balancing the force of gravity in the vertical direction or in the y direction. This tension is distributed along the Slinky's length, with the upper coils supporting the weight of the lower coils. This balance prevents the bottom of the Slinky from moving as long as there is tension in the Slinky. Thank you very much, guys.